All right, what we're going to look at today here is scientific notation and the concepts of precision and accuracy. Now, I know scientific notation is something that you've covered before, so this should be review for you. Scientific notation is a way of writing either very large or very small numbers more conveniently. And there are two distinct parts to numbers in scientific notation. The first part, and this is often the part that students will mess up from time to time and make mistakes on, this needs to have a number with a decimal point, and it has to be greater than 1 but less than 10. And those are the rules. It can't be greater than 10. Okay, it also has to be at least 1. The second part is a power of 10. And that power of 10 will either have a positive or a negative exponent. And what that shows when a number is written in scientific notation, if we're changing it back into long form, is which way and how many places we would move the decimal. The negative sign tells me that I'm dealing with a number that is less than 1, and the positive number or positive exponent would tell me that I am dealing with a number that is greater than 1. So for example, if I am given this number, 1 times 10 to the 6th, simply by looking at that power of 10, I know that if I change this number to the long form, that it needs to be greater than 1. So in order for it to be greater than 1, if I look at where my decimal point is, I need to move it to the right. So because the exponent is positive, I am going to jump the decimal 6 places, because that's the exponent number I have, and I'm going to move it to the right so that my resulting number is greater than 1. So the number that I would come up with that is 1 million. So let's take a look at the general rules here with scientific notation. For any numbers that I have that are greater than 1, I have a positive exponent. So when I have a positive exponent and I'm turning a long number into scientific notation, I'm going to move the decimal point to the left when I put it into scientific notation. When I take it out of scientific notation, I have to move it to the right, like I just showed you. So let's take a number, 86,000, and let's put that into scientific notation. Remember, the decimal point is here after that last 0, even though we don't see it. So we would jump at 1, 2, 3. Now, if I stopped here, I would not have correct scientific notation. I have to jump at that 4th spot in order to get 8.6. 8.6 satisfies my rule for the first part to be less than 10, but more than 1. So my answer would be 8.6, and I jump the decimal place 1, 2, 3, 4 places times 10 to the 4th. Now, for numbers that are less than 1, I have a negative exponent. And when I take a number that is less than 1 and put it into scientific notation, I am going to move my decimal to the right. If I'm taking it out of scientific notation, I'm going to move the decimal point to the left. So let's take this number here, and there are 1, 2, 3, 4, 5 zeros after the decimal point here, just because I know it can be hard to see. All right, we're going to put this number into scientific notation. So I'm going to jump that decimal point 1, 2, 3, 4, 5, 6 places, so my decimal point ends up between the 9 and the 7. So then my number would be 9.7 times 10 to the negative 6. Then again, that negative exponent tells me my number is less than 1. Now, in your homework for tonight, you are going to be taking numbers out of scientific notation and writing them the long version and putting them into scientific notation. But you need to remember that you need to put them into scientific notation correctly, following those rules. Now that's a little bit of review, but the second part here deals with two terms that I've actually been using already, precision and accuracy. And those are tied in with our discussion about measurements. Precision is the first one that we are going to talk about. Precision is a gauge of how exact a measurement is. Now that can be confusing, especially when you think of accuracy. So I actually like this second definition better. How well that measurement can be reproduced or replicated. So in other words, if I take the measurement of something 5 times, how closely do those values represent each other? In other words, how close are those values to each other? Kind of for my visual learners out there, you can think of it as a bullseye target that looks something like this. You can see here that these 3 bullseye shots, while they're not very close to the standard, what we want at the bullseye, they are very close to each other. So whatever was used to fire these 3 shots is very precise. Now let's compare that. Let me give you another example here. A digital clock is more precise than an analog or a regular clock with the hands. In other words, the chances of us interpreting the time the same is going to be greater with a digital clock than it is with a clock with just hands. Now, let's contrast this with accuracy. Accuracy is how close a measurement is to the actual accepted value. So in other words, we have an accepted value for something. How close is that measurement to it? That tells you how accurate it is. Usually when we are trying to determine accuracy, we take an average of several measurements to produce as close to that accurate value as possible. Again, we can give a visual representation. You can think of a target that looks like this. Now again, when we're shooting at a bullseye target, our goal here is in the center. Now my shots are a lot further apart than they were with my precision, but you can see they are a lot closer to the target. In fact, if I took the average of those shots, it would probably end up somewhere around in here, which is very accurate. So in this case, this set of shots are very accurate, but they're not very precise. In my other set of shots, they were precise, but not very accurate. If I moved these shots in closer to each other, I could actually have both precision as well as accuracy. So again, another example here would be with time. An atomic clock is more accurate than our school clocks. In other words, an atomic clock produces a time value that is closest to, or the accepted value for time, than the clocks in the school do. Now again, you have a worksheet that will be homework for tonight that will actually talk about have you working with accuracy and precision and apply it to a miniature golf game.